All right, section 2.2 we started last time. We looked at some information about sets and counting objects inside of sets. That's actually where we left off, was with what we called cardinal numbers. Cardinal numbers are simply the number of items in a set. So we had left off on taking a look at what were called Venn diagrams. Venn diagrams are diagrams that are used to illustrate ideas in logic. Within a Venn diagram, there is an object called a universal set. It's the set that contains all elements being considered in a given discussion. And then the complement is if you have a set inside of the universal set, it's the stuff that's not in it. I joked in my last class that describing something by saying what it's not is one of those weird things, and we do it a lot. Right? It's not this. That's how we define it. Because sometimes it's easier to look at something and decide what it's not than what it actually is. So let me show you a picture of what this is actually describing. A universal set in a Venn diagram always starts out looking like a rectangle. Okay, so draw yourself somewhere on your paper a rectangle. Don't make it too tiny because you're going to draw stuff inside of it. The rectangle is the universal set U. Everything in the universe of whatever your discussion is about is inside the rectangle. So there is no outside the rectangle. All right? There is no outside the rectangle. Inside our rectangle is our universal set. Within the universal set, we have circles. And our circles are, potentially at least, other sets inside of there. So I'm going to draw a circle or an ovalish shape. And because it notated it as F, we'll call it F here as well. Okay, given a set F, this is all elements. Okay, so the complement then is the stuff that's inside the rectangle but outside of F. And that is actually written with the letter F and a line on top of it. Now, that's not the only way that this can be written, but it is your notation for your book. So let me show you a couple other notations that you might run across if you were to Google something about this, or if you were to watch somebody else's YouTube video or something like that, and you're like, what's that notation about? Another one that they will sometimes use is they will use F with a little, like an accent mark, you know, or an apostrophe kind of mark, like that. Or a third option is that sometimes they will do an F with a little C above it, which I kind of like that one. F complement. A little C up there. So your book uses the first one, so we'll use the little hat with the, the line on top notation. That's what we're going to use. Okay? Complement. So visually, in this diagram, F complement is out here. I'll shade in F complement. Okay? So this piece right out here, all that's shaded in yellow, that's F complement. Everybody good so far? So, if we were doing an example, we might talk about, for instance, my family, because I like to talk about my family, I know them. So my family is all of the universal set, and the circle is all the females. That means the piece on the outside would be all the males. Okay? That's the deal. So, we're going to do an example now with words. U is the universal set. It's the set of all students at OBU. And A is the set of those who are graduating. So what then would we describe as a complement, or the complement of A?
All the students that are not graduating.
Yeah, all the students at OBU who are not graduating, right? That's who this would be. So we'll write that down. A complement is all OBU students who are not graduating. Okay, so we talked about this set inside of the universal set, but we can also have a subset, which means a set inside of another set, so sort of embedded circles, you know, concentric circles. A subset. So for all sets A and B, we would say that B is a subset of A if and only if every element of B is an element of A. subset notation to say that B is a subset of A looks like B. It's sort of a sideways U or kind of a flattened looking C with a line underneath it. B is a subset of A. You can kind of think of it as almost like a letter C. You can also think of it as saying B is contained in A. It resides inside of. So visually, it would look, if I had my Venn diagram, like a circle inside of a circle. All right? So here's the universal set U. My set B is inside of set A. Now, you'll notice that there's a line underneath it. Do you remember when you did inequalities in algebra? You had less than and you had less than or equal to, right? So the less than or equal to meant that it could do one of two things. It could be less than it, or it could be equal to it. And this notation is much like this. It could be C contained in it, or it could be equal to it. So in other words, it is possible to have this description, albeit odd and weird, to say that B and A are the same set. They're exactly the same, and then one of them's a subset of A. One of them's a subset of the other one. So I could talk about, for instance, my family, where I live, my husband's family, where we live together, so it's the same people, okay? Just clarify that real quick, okay? So, and if I say that my family is a subset of my husband's family, that's true. I mean, they're equal, so it's weird to say that, but it works, because every element of my family is an element of my husband's family. That makes sense? If we wrote down all the people inside of both groups, it'd be the same group of people, as long as we wrote our own names. It will work. A proper subset, however, has one extra condition. So for all sets A and B, B is a proper subset of A. If and only if first it has to be a subset. Well, that sounds pretty good, right? And then it has this word proper. What does that mean? Well, the word proper means that there's at least one element of A that's not in B. It means that A really has to have more in it than B. So visually, you have the same picture that you had before. Notationally, we just leave off that line below the equals. Right? So when you talked about in algebra, if x is less than 5, that means it can't actually be 5. Here, without the equal sign underneath, it means they can't be equal. It's not a possibility. So it's not a correct statement to say that my family is a proper subset of my husband's family. It doesn't work. Cool? Okay. Counting subsets. So if a set has n elements, then there are 2 to the n minus 1 subsets. I'm sorry, 2 to the n subsets and 2 to the n minus 1 proper subsets. I'm going to show you an example of this here in a second. So just jot them down as the numbers for now. Okay? We're going to do a very small case example because the numbers get very big very quickly, right? 2 to the n, 2 to the 4th, I've already got 16 things I have to write down. So I'm just going to do 2 to the 3rd. So we're going to do a set with 3 elements in it, and I'll show you how this works. All right, I have space on this slide. I'm just going to write it at the bottom. It's not what this slide says. We'll come back to what the slide really says in a second. But let's say that we have the subset, or the set, excuse me, with the items 1, 2, and 3 in it. And we want to write down all the subsets. Okay? All the subsets will include the set 1, 2, 3. Right? A set is a subset of itself. Sounds weird, but remember it's got that equal sign part of it, so it counts. So when we're writing down our subsets, 1 is the whole thing. Now we're going to write down all the subsets that are smaller. So if it doesn't have 3 elements, it could have 2. Agree? So I could have elements 1 and 2 in my set. What else could I have? 2 and 3. What else could I have? 1 and 3. And that's all the ways of writing down a subset with 2 items in it, correct? Everything else would repeat it. Maybe a different order, but it would repeat the actual same group. Okay, but maybe I don't have 3 elements or 2 elements. I only have 1 element. Okay, well that's set 1, set 2, or subset with just 3 in it. There's one more that I'm missing.
The empty set.
The empty set. And I know it sounds weird to say, but everything in the empty set is in the set with 1, 2, 3. And hopefully you're looking at it and saying, well, I mean, yeah, okay. Right? I mean, it sounds weird to say that. There's nothing in the empty set, so how can we even talk about it like that, right? There's nothing in there. But remember we talked about the null set last time? Those wonderful little babies that live at my house? Infants, right? The babies, they're fantastic. They clean their own diapers, stuff like that. Yeah, right? We talked about them. Right. The babies that live at my house, they're fantastic. They're wonderful. And they're a subset of the people in my family. There's nothing in that set. I get that. But because there's nothing in the set, it fits the definition. Because the definition says every element in that set, the empty set for which there are no elements, is by default in the original set. Count my subsets. How many do I have here? 8. And 8 is the same thing as 2 to the 3rd power. So there are 8 subsets. One of them is not a proper subset. Which one's the non-proper subset?
1, 2, 3.
The 1, 2, 3. This one would be not a proper subset because it's actually the same size. It has to be smaller, right? So the rest of them would be 2 to the 3 minus 1, which gives me 7. The minus 1 is after the power, not within the power. Okay, minus 1 on the bottom here would be 7 proper subsets. We could repeat this pattern if we would like to for bigger sets or different sets, but it'll always work. 2 to the n minus 1. So let's take a look. Consider the set of all mathematics faculty members at OBU. And if you're not sure, there are 5 of us. Does anybody know our names? You know mine. Dr. Hands. Who else am I missing?
Dr.
Dr.
Auk.
Auk.
Dr. Marsh.
Dr. Marsh.
Dr. Tucker.
Dr. Tucker. Very good. Dr. Bond. That's the last one. Have you had Dr. Bond?
Yes.
What'd you have him for? College algebra. You had college algebra. Okay. So there's 5 of us. 5 math faculty. And it says how many different subsets are there of the math faculty? Okay. So smaller collections, equal collections, how many are there? So I could write them all down. I could write our 5 names, and then I could actually collect us all in groups of 1, in groups of 2, in groups of 3, in groups of 4, in groups of 5, and a group with nobody in it. Or I can use this equation, right? Not equation, expression, formula. So there are 5 of us. So what would I do to find the number of subsets? 2 to the 5th. 2 to the n with n equal 5, right. So what is 2 to the 5th? 32. How many different proper subsets are there? 31. Okay? Fantastic little formula there, right? Really is. All right. We're going to do another example that's a little bit backwards feeling. It says, suppose that you have a set, and what you know about the set is that it has 63 proper subsets. How many elements would there be in the set? So we don't know n. We're looking for n. You guys with me? N is the number of elements, and that's what we do not know. So what we do know is that we're looking for 2 to the n. Well, we're looking for the n part of the 2 to the n. But we're told how many proper subsets we have, so we're actually told something about 2 to the n minus 1. What are we told about it? It's equal to 63. So think about solving this. You don't have to necessarily do this with algebra and so forth, but probably the first step you should be okay with. How about we just add 1 to both sides? Yeah? So we want 2 to the n to equal 64. You can play with your calculator to figure out what that n value would be. 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8, 2 to what? What does it take to give me 64?
6.
It takes 6. So there are 6 elements. All right. We're going to do a few fill in the blanks. Whenever I ask this type of question, whether it's this example number 7 or example number 8 on a test, I will ask you to justify the answer as to why you put what you did. Your book doesn't ask you to do that on their problems, so you don't have to, but it better be something that if you look at it, you remember why you said what you said. Otherwise, it's going to be less than helpful when you get to the test and you can't figure out how to write that down. Does that make sense? Okay, so we're just going to fill in the blank. This problem says to indicate which symbol would be true in the statement. This symbol means what? Is an element of, and I haven't actually explained this one, but what do you think it means when I put a slash through it? Is not an element of, okay? So one of these two symbols will go in each one of the blanks. It's going to be one or the other. Make sense? We got to pick which one fits best. So there's two things in determining if something is an element of something else. You first have to figure out, is it even an element, like at all? Okay, that's one thing. And the second thing then is to decide, is it actually contained in the other side? Is what's on the left contained in what's on the right? Okay, is it something that's actually a member of that group? So let's take a look at the first one, part A. Part A has what on the left? Empty set. First question to ask yourself is that an element? No, it's a set. Right? You called it the empty set. It's a set. And if it's a set, then it's not an element. So you don't even have to ask yourself about the containment principle or part of this problem because it's not an element to begin with. Right? This is what happens when Dr. Out comes in and he says he's a mom. You don't even have to entertain the question because he's a man, right? It doesn't work. This is not an element, so it can't be an element of what comes next. Second one, part B, 15. Again, asking ourselves, is this an element of something? Is it an element? Yes, it is. It's an element. Then we need to figure out if it's an element of what comes next. So look at what comes next. This is set notation, set builder notation, which we talked about last time. Remember it says x such that, and then it tells us how things are defined. X equals 2n, and n are the natural numbers. So what are natural numbers? 1, 2, 3, 4. And when I put those numbers 1, 2, 3, 4 inside of the 2 times them, what numbers do I get? 2, 4, 6, 8. And what are those called, Rebecca? Even numbers. So this piece right here tells us my n values are 1, 2, 3, 4. And then this piece right here tells us what this set actually is by taking the numbers 1, 2, 3, 4 and putting them in. I get 2, 4, 6, 8, and so forth. And i.e. evens. These are the even numbers. So, is 15 an element of this set? No. It's an element, but it's not even. So this one is not an element, but for a very different reason than the first one, right? Very, very different. So if you were explaining the why on this on a test, it would look quite different as to your why. The third one, part C. Is this an element? No. What makes this different than the last one, Catherine?
It has the curly braces around it.
Right, those curly braces. Those curly braces make it a set. It's set notation, right? So this one is not an element of, because it's not an element at all. It's a set. So the answer for why this is not going to work is much like the very first problem. It's not going to work because it's not an element. How about part D? Is what's on the left an element? Yes. And you might, at this point, be tempted to say yes because it doesn't have curly braces. And that wouldn't be altogether false, right? It doesn't have curly braces, so it is an element. Is it an element of what comes on the right? Yes. What's on the right? Even numbers. It's described differently than in part B, but it's just the even numbers, and 16 is in fact an even number, so this is an element. Okay, everybody good with that? Two questions to ask yourself. Is it an element at all? And then is it something that's actually contained in what the other piece is on the right? All right, similar question, but what's different here?
Asking if it's a subset.
Yeah, the symbols between them ask us about subsets instead of about elements. So the first one means it's a subset, which means it could be equal to it even, right? That would be okay. The second symbol, again, which I didn't define, but you guys are super smart, and you know what that means. What's it mean?
It's not a subset.
It's not a subset. Anytime we put that slash mark through something, it means not, right? Yeah, it's not a subset. Okay. So, again, you're going to have to ask yourself to start with. In order to be a subset, it first has to be a set, and then it has to be contained in. All right, so the difference in these two questions, number 7 and question number 8, or example number 7 and example number 8, is what's on the left a set or is it an element? On the last one we looked at is it an element, is it an element, is it an element, and now we're looking at is it a set, is it a set, is it a set? And then I can look at the containment issue. So the first one, part A, is what's on the left a set?
Yes.
Yes. And I know it doesn't have the curly braces, but we know that this is that special one. It's the null set or the empty set. So it is a set. Okay, so half the battle is already won. It's a set. On the right, now we have to determine, is the empty set actually contained in what's on the left or on the right? Yes. Here's the cool fact, and you might want to write this down so you have it in your notes. The empty set is always a subset of every set. So this one works. We'll write the subset notation, kind of the squished C and a line underneath it. Always. I don't care what's on the right. The empty set is always a subset because to be a subset it means it's a set. We already said that. And everything in it is in the other piece. And everything in the empty set is in every set. Because there's nothing in it. Right? All right, part B. Is what's on the left a set?
No.
No. How do you know it's not? No curly braces, right? It's an element. So this one fails because it's simply not a set. Third one is what's on the left a set? Yes. Okay, so now we actually have to look at it. We didn't have to look at it last time. The set with 4 in it. Now we look at what's inside of the curly braces. What do we have that's in there? It's a 4. That's the only thing that's in there. Is the number 4 inside of what's on the right?
Yes.
Yes. What is the set on the right actually the set of? 3, 4, 5, 6, written funny, but that's really all it is. It's the set of 3, 4, 5, 6. And is everything in the set on the left in the set on the right? Yes, it is. So this is a subset. Not only that, but we could actually write were in the directions to allow us to do so that it's a proper subset, right? It's actually smaller, too. So the part on the bottom isn't really necessary. It's not wrong that it's there. It's just that it's really not necessary. It's not smaller than at all. I mean, it's not equal to at all. It's really smaller than. D, is what's on the left a set? No. So this one also fails to be a subset because it fails to be a set. All right. The next thing we're taking a look at is one of these keywords in mathematics. It has the word fundamental in it. Fundamental usually means it's pretty important. It's fundamental. It's super important. We talk about this with our faith, the fundamental principles of our faith. So when I was hired at OBU, they wanted to make sure that the fundamentals of what I believed are what the fundamentals of OBU believes, right? Whether I'm a Southern Baptist or not, do I believe the same fundamental principles about my relationship with Christ? Fundamentals. Same thing for math. Fundamentals of what's going on. So, fundamental principle of counting, fundamental counting principle says, if you have an event M that can occur in little m number of ways, and you have an event capital N that can occur in little n ways, then the event M followed by the event N can occur in mn ways. And our first example has clothes in it because that's a really good example actually. So presuming that everything of this collection matches, which is an awfully big assumption to start with, right? Yes. We're going to figure out how many outfits we could actually pick out. Or you could just not match. One of my daughters doesn't care if she matches. I think she thinks it matches. And apparently that's really the style now, is to not match a lot of things. I don't know. It's very strange to me. Okay, so we have 3 shirts, we have 4 skirts, and we have 5 pairs of shoes. And our assumption is we need one of each of these things. Okay, so we're not going to wear 2 pairs of shoes or something like that, because that would be weird. We're also not going to wear 2 shirts, although that would be less weird. We're just going to wear one. Okay, outfits. So what we're going to do is we're going to take, according to the fundamental principle of counting, the number of shirts, which is 3, times the number of skirts, which is 4, times the number of pairs of shoes, which is 5. And if we multiply all that out, that will tell us how many different outfit combinations we could make with this set of clothing in our closet. So what is 3 times 4 times 5? 60 outfits. So you guys, we talk about this in proportional and statistical reasoning as well. And an example I always like to talk about there, and we won't do the example here, is Sonic. At one point, Sonic talked about how they had 1 million something or other. I don't even know if that was the number, but they had this astronomical number of different drink combinations in Sonic. And they did something a lot like this. They multiplied out how many different, if you did 1 flavor in your drink, you could get. How many different, if you did 2 flavors in your drink, you could get, and so forth. And if you combine all of that together, you get the number of drink combinations at Sonic. And it's using the fundamental principle of counting. All right, so let's take a look at a variation of this, because now we've got some clothing and we decided 120 outfits, or I'm sorry, 60 outfits. Was that what we had? 60 outfits, yeah, was not enough. We need to go to the mall and buy some more. All right, so you have 6 favorite stores in the mall, and we want to know in how many ways you can do the following. The first one, part A, says you have time to go to only 3 of them. Okay, so when you're going to them, you have to choose where you go first. And the first place you have is you have how many choices? 6. And then our second location, we would have how many choices? 5, because we wouldn't go to the same store again, because that wouldn't make sense, right? And then our third choice, we have how many choices? 4. So if we take 6 times 5 times 4, what will we get? 120. So there's 120 different options we have of which 3 stores to go to. Ways, 120 ways. What if you have time to go to all 6 of them? What would you do? That's right, 6 times 5 times 4 times 3 times 2 and then times 1. And what would you get? 720 ways that you could go to your 6 different stores. This actually has a special form. The last one we did, it's called a factorial. We don't do that in this particular class. We do that for proportional statistical reasoning, but it does have that notation notated with it as well. You might also notice that we've seen this before. I know it's been 2 days since we did it, but if you flip back in your notes, we did this when we did one-to-one correspondences. Remember we were talking about my family and y'all's families, right? Rayleigh and Rayleigh's families, and they're all the same number of people. And we did these correspondences, and we said there's a pairing. We do 6 people options, and the second person has 5 options, and so forth. I think we were going to 6 Flags, weren't we? That's what we were doing, yes. All right, last example. I want you to create a real-life example in your life of the null set. I gave you my example. My example is the babies in my house. I will tell you that effective 3 years ago, my example had always been the teenagers in my house, and I can't use that anymore. There are now 2 teenagers in my house, and there's about to be 3. Well, I mean, it's in a year, but that's close enough, far too close. So, can't use the teenagers in my house anymore. I'm using babies now. These days, I'm using babies. So, I would like for you to write down an example of a null set in your life. Okay? So, write something down on your paper. You can choose whether or not you say it out loud. I'm not going to make you. But write something down. It's a null set in your life. Okay? Everybody should have something. So this is a volunteer only. I'm not picking on anybody. But does anybody like to volunteer what they wrote down for their null set?
The number of Justin Bieber songs on my iTunes.
Okay, so let's fix one piece of what you said. This is why I want you guys to say. We don't want to use the number of.
Okay.
We would just say the Justin Bieber songs on your iTunes. Yeah. Okay, good. What's another example? The cats that live in your house. See, that wouldn't be a null set in my house. But that works for you. Fantastic. Cats that live in your house. One more.
My sisters.
Sisters. So you must not have any sisters, right? Fantastic. The one that I almost always get, and you guys you let me down today, is I usually get somebody saying something like, my boyfriends. So do you have that? My boyfriends. Yeah. Did you have that one down, Beth? Beth? She just didn't want to say it. Suitors. I like that better. That's such a nicer term. Your number, not the number of, but the suitors. Fantastic. All right. Thanks, guys.